Okay, so this starts kind of the second half of, if you would, our lectures here for Module 11. So starting at the very beginning here of Part 2 PowerPoint presentation. Okay, this is the second PowerPoint presentation. Our first slide wants us to do sample problem 11.6, and this is found on page 642. So actually, I don't have that one here, so I'm going to go underneath. Okay. And on page 642, you're going to find that little ways down on the page, this is where we have our problem statement for sample problem 11.6. So here we have a car. Car A is traveling at a constant 90 miles per hour. Okay, 90 miles per hour. When it passes a parked police officer in car B. Okay, so here's car A moving along, kind of going fast, passes a police officer, okay, who is at rest. All right. Um, who gives chase when the car passes by. So they're like, all right, you're going a little fast, maybe a lot fast. 90 is pretty fast. And they're going to, probably have a little discussion about that. So the officer accelerates at a constant rate until reaching a speed of 105 miles per hour. It's pretty fast too. Thereafter, the officer's speed remains constant. All right. The police officer catches the car at the 3 mile mark from the starting point. They want us to determine what was the initial acceleration of the police officer. So here again, we have two elements. So we have one item relative to the other. We have different conditions for each one of the cars. So we're going to start out by kind of identifying what we know. And then we're going to get into, solving for that acceleration. We'll see the process that we go through. Okay. So, I think I'll kind of come back to this. So we'll start by doing our givens. Okay. So this is sample problem 11.6. Okay. And this is on page 642. Okay. So as we know, we have two vehicles. We've got car A, all right? And car A is the 90 miles an hour, and it's saying that it's going at a constant 90 miles per hour. So that means that this is a constant velocity condition. So I'm just going to put that here, constant V, okay? We know that the velocity of A, starting, middle, finish, is going to be 90 miles per hour, and it's going to the right. Our positive convention is going to be going to the right. So anything that's going that way, it's going to be positive. Because it's at a constant constant velocity, our acceleration of A is 0. Okay. And then we know that distance-wise, from where the car passes the police officer to where the police officer catches up, this is 3 miles between there. Okay. So we can say that the final position, X, because it's horizontal, we'll reference it as X, is equal to 3 miles. Okay. And that's where it meets RB, right? So let's talk about B. And that's going to be the police car, right? The police car, as we look here, it has like two phases. There's a part 1 and a part 2, because remember, the police car is going to speed up, speed up, speed up. So it is going to have a constant acceleration until it gets to 105 miles per hour. Okay. Once it gets to 105 miles per hour, then it's going to go at a steady, steady, steady rate. Okay. So what they're doing is they're referencing this first distance to where the police officer gets to 105 as X1 for that car. Okay. And then T1 for when that happens. Okay. So we look here, we have the original velocity, or the initial velocity of our police car, is 0 because side of the road starting at rest. Okay. The final velocity of our police car, actually, I want to do it this way. I'm sorry. BO and BF. So we'll put the B next to the variable. The final velocity of our police car is 105 miles per hour. Okay, and it's again going to the right, it's positive. Acceleration of the police car, we don't know, but we do know it's constant. Okay, it's constant. We don't know. And this right here during this time, this is during the T1 time, first chunk, part one, and the X1 time. And we will see when we do the work, we're going to break it out into part one and part two because there are two parts here for car B. Okay. Now we're gonna have to find what X1 is. I don't know. We don't know what that is. We'll be calculating that. That's gonna be the time that ends acceleration. Okay. That's when it gets up to that 105, and then it's going to be steady after that. And then we also know that the final position is equal to that 3 miles. And that's when it catches up to car A. All right. And we know we can also say the relationship here, the A final is equal to the B final. That's that 3 mile mark. Okay. So these are kind of our givens, right? And a little bit of the finds, right? Okay. So we need to find that acceleration, you know, that car B is going. And then there's a couple little things along the way too that we'll be doing, but the problem is asking for that. Okay. Now, first things first, we have to look, just like we did for the previous problem, is we got to look at our units. First of all, determine are we English or metric, and then we want to get everything in consistent units. So are we English or metric? Anyone?
English?
Tyler says English. I don't know who said that, but yes, English is correct. It's English because we're dealing with miles, right? So when we're dealing with miles and not kilometers, kilometers would be metric. That means that we are going to be dealing in the English system units. Now, when we start looking at velocities and accelerations, okay, even though it's given in miles per hour, we want to make all the units consistent, and we want to make them all in feet and seconds, okay? So our units, we want in feet for distances and seconds for time, okay? Or I'll do and seconds, feet and seconds. And we're in miles and hours, okay? So the first thing we're going to do is we're going to convert, you know, anything that we have here. So step number one is convert. All right. We want everything to be consistently in feet and seconds. All right. So our first one here is we are going to convert the 90 miles per hour. Okay. The 90 miles per hour. So velocity of A is equal to 90 miles per hour. Remember, we're going to use the ratio method so that you show the cancellations. I don't want anybody just, you know, putting a calculator online and like, oh, here's the final number. You got to show me any conversions that you do as well. And they're going to be in the ratio format that we've done in other courses. Okay. So 90 miles per hour. So miles is on the top. We want to get that into feet. How many feet are in a mile?
5,280.
You got it. Thanks, Brett. So 1 mile is going to go on the bottom here because we got to multiply across the top, divide by the bottom. So miles need to be opposite. And then directly above, we're going to do the 5,280 feet. If you need to look that up, that's totally fine. But that's one of the popular ones that some people just end up knowing, right? 2,000 or 5,280. Perfect. So cancel out your miles. So now we're in feet per hour. We want to get to feet per second. Feet per second. So do another. Hours is in the bottom here. Remember, when we're miles per hour, the per is our horizontal line for our fraction, and the hour is in the denominator. So since it's on the bottom, hour has to go on the top. So we're going to put 1 hour on the top. How many seconds are in an hour? Anybody know offhand?
3,600.
That's correct. 3,600 seconds in 1 hour. So now top to bottom, hours canceled, and we have this in feet per second. So you're going to multiply across the top 90 by 52 times 5280 and divide by 3,600. And what do we get for our velocity of A?
$132 feet a
Yep,
second.
132 feet per second. Yep. And put the units in there because this is now whenever we are going to be referencing A, we're not going to use the 90, we're going to use the 132. Okay? The next one we want to do is the 105, okay, miles per hour. So this was the velocity of B final at that first part. So that's going to be 105 miles per hour. Okay. So here again, we're going to do the same ratio. So we're going to have 5,280 feet on top, 1 mile on the bottom, miles cancel. And then we're going to have 1 hour on top, 3,600 seconds on the bottom. Hours cancel. Make sure you cancel. Because if you don't cancel it out, you don't know what's left over. All right. So I will be watching for that in your equations or in your calculations. So for this one, what do we get? Get 154 feet per
I
second.
did.
Okay, perfect. Anybody else as a confirmation? I'm pretty confident. Okay.
I did too.
You got it too? Awesome. The last one that we're going to do is we're going to convert the 3 miles, okay, to feet. Okay. So this is going to be XAF is equal to XBF is equal to 3 miles. And this one's easy because that's just simply going to be over 1. So then we're going to put our 1 mile on the bottom and 5,280 feet on top. Miles cancel. Okay. And that's going to be equal to 15,840 feet is equal to XAF and XBF. That's that 3 mile, oopsie, box. It's going to be a cloud. Okay. So again, instead of 3 miles, we're going to use this value. Okay. So another little separation because the conversions are kind of like, okay, this is setting things up. And this also ensures that as we do our problems, we won't have to. We know that our units are all consistent. We don't need to worry about doing any units inside of things. Okay. Okay. All right. So now we're going to look at the motion of each one of the cars. So we're going to look first at the motion of car A. All right. So the motion car A. Okay. And we already know that car A is speeding at 90 miles per hour and it's going at a constant rate. So this again is going to be constant velocity. Okay. And when it's constant velocity, we are in this area right here on our equation sheet. Okay. So we know that to define our motion, our velocity anywhere for A, I'm just going to call it velocity A. It's the initial, it's the final, it's the middle, it's all of them, is going to be our 132 feet per second. Okay. So whenever it's referenced, that's what we're going to use. And then we also know that our final distance is going to be the 15,840 feet. Okay. So if we want to calculate a distance anywhere, or I'm sorry, time. Yeah, we can already do that. So if we look at the equation relating distance, time, and the velocity here, because we know both distance and velocity, and we can then calculate for the time, we are going to use the middle equation here. Okay. So our X AF, which is the 15,840, is going to be equal to the distance from the original distance from the origin, okay? Well, when we look at our diagram, the origin is right here, and this is where we're starting, okay? That's exactly where we're at. So this is going to go to 0, okay? That's where we're kind of analyzing the problem. Everything is starting there. Plus our velocity of A times the time, okay? So since we know that we want to find out what is the time that it takes for our car to get to that 3-mile mark when the police officer catches up to it, we're going to put the 15,840 here. And then we also know that it is going at a steady 132 feet per second. So our only unknown variable here will be the time, okay? So let's go ahead and put the 15,840. It's going to be equal to 132 times time. And solving for time here, our time is going to be equal to 120 seconds, okay? Now, it's not asking us as an answer for that time, but we're going to need it, all right? So this is the time to travel the 3 miles, okay? It's at the end of the path, if you would, for car A, right? Any questions so far? All right. If not, then let's look at the motion of car B, okay? Motion of car B. Car B, let's see. And car B is the police car, okay? Now, the police car has 2 parts, okay? As I said earlier. So part 1, we're going to look at first. This is the constant acceleration phase, okay? The constant acceleration phase for our police car is from when it starts from rest until it gets to that 105 miles per hour. Okay, so this section right here, this is part 1. Okay, so part 1 is constant acceleration. All right, and that's going to be from, we're going to call that time 0 or initial time to T1. Okay, so we're calling this X1. So that means the time that it gets to that point is going to be T1. All right, and I'm going to say at 105 miles per hour. Okay. Now, we're not going to use 105. This is just a reference based on the description of the problem. Okay. So now, since we're in constant acceleration, okay, we want to define the motion by the equations that we see here. So the first one we're going to look at is the first one here, because we know what we're going to be finding the acceleration. That's going to be our problem. And we know what our, velocities are starting and finishing. So we're going to have velocity B final. It's going to be equal to velocity B original plus the acceleration of B, which we don't know and we're going to be solving for, times time 1, because we want to know just in this chunk right here, okay, how much time does it take to get to that 105 miles per hour, okay? So based on our numbers here, our velocity of BF, bring our sheet back. Here again. Our velocity BF in feet per second is 154. That's our number, okay? So 154 on this side. Our original, this is starting from 0. So this just goes to 0, okay? Because remember, the police car is at rest on the side of the road, okay? So it starts at 0. Acceleration of B is an unknown variable, so we're just going to leave it at that. And then this is going to stay at T1 because we don't know what that is yet, all right? Now, because we know that we need to know, it's asking what is the acceleration of B, we're just going to rearrange this. So the acceleration of B is equal to, I'm just rearranging this equation, 154 divided by T1. Okay, and we're just going to let it sit there just like that because there's 2 unknowns in that equation. We can't go any further. Okay. Now, the other part of the motion that we want to know about, again, we know we're going to be finding that acceleration. We're we're going to, find, we know what that final velocity is, but now we've got to do position, okay? So let's work on that. This is going to be our XB1. So this is part one. So we want to know what is this distance right here? Okay, that X1. And I'm calling it B because that's for car B. So B1 is going to be equal to its distance offset from the origin, which is going to be 0, plus the initial velocity B0, sorry. The initial velocity, which was from rest, that's going to be 0 times the time. Okay, so this is going to be 0. This is going to be 0 because we're starting from rest and we're starting where the problem is starting. So there's no offset from the origin. Plus, sorry, 1/2 acceleration of B, which we don't know, times time 1, okay, that first chunk squared, okay? So our position B1 is going to be equal to 1/2 AB T1 squared. So we really don't know much here, all right? And again, this is the distance that it takes to get to that 105 miles per hour to complete part one of the police car's ride, okay? Let's look at part two, okay? After the police car gets to 105 miles per hour. So part two, okay? Now, the police car gets to 105 and it's going to go at a constant rate, okay? A constant rate. So what that means is part two is constant velocity, right? Constant velocity. So our acceleration B2 is equal to 0. All right, there is no acceleration after the police officer gets to 105. Okay, now the time here is going to be from T1 to T final. Okay, and that T final is at that 3-mile mark. Okay. Now, we already know this time, don't we? We know that time to be 120 seconds because we calculated using car A, who was going at that constant velocity, and at that 3-mile mark, it took 120 seconds. So we can say this is 120 seconds. We know that already. Okay. Now, the rest of the motion. The distance, we're going to call this B2, okay? It's going to be this chunk right here, B2. It's going to be equal to our velocity final at B, okay, which is the 105 miles per hour or the 154 feet per second, times T final minus T1, okay? So because the total time is 120 and T1 is to here, this is the time in between. So it's that difference, okay? Because we're just looking at part two. So we don't know XB2. That's going to be equal to, because that's that chunk. But we do know that the velocity of our police car is 154 during this section, uniform. And then we do know that that final time is 120 seconds all the way to the end minus T1, okay? So if we look here and we multiply, we distribute that 154, we're going to get XB2 equal to, and double check my numbers here, 18,480 minus 154 T1. And that's where we stop. Okay. Just a confirmation that somebody got that number.
I did.
All right, you got it, Nia. Thank you. Okay, thank you. All right, so now what we're going to do is we're going to take and we're going to say, okay, BF final, okay? It's going to be equal to, now XBF, I'm sorry, XBF is going to be the position, the final position of the police car and our car. That's that 3 mile mark. Okay, that's the 3 mile mark. I'll just add that 3 miles. Okay, that's going to be equal to our XB1. That's the distance that the police car covered in part one, plus XB2, the distance that the police car covered in the second part of its travel. Okay. So we know that the total distance is 3 miles. We know this to be 15,840. 15,840, and that's feet. So if we look back at our conversion that we did the 3 miles, 15,840 feet. Okay, that's where that is here. Okay, so don't put 3 in there. We're putting the feet in there. It's going to be equal to, and if we look at the equation for XB1, it's right here. That's going to go right down here. So that's going to be 1/2 ABT1 squared. Okay, so that goes right down there and it's going to be in its place. Plus XB2 is right here. 18,480 minus 154 T1. So now what we have is we have an equation that just has T1s as their unknown variables. Okay, but the T squared kind of puts a little wrench in it. Okay, now if we recall from our previous sheet, I'm not seeing it. Oh, no, it's up here. We know that AB is equal to 154 divided by T1, okay, because we got that there. We're going to use that in this place right here, all right? So we're going to say 15,840 is equal to 1/2, and instead of AB, we're going to put 154 divided by T1, okay? And then we're going to multiply that by T1 squared. Now we're going to do our plus 18,480 minus 154 T1. Okay. Now, because, separate that a little bit, this is T1 and this is T1. One of these T1s cancel out just one of those. Okay. So now, now we can kind of do our distribution and our multiplying. So I'm going to send this to the other side. This is going to become 0. Then we're going to take 1/2 times 154. That's going to be 77. And then the variable here is just going to be a T1. Okay, because that one canceled out. Plus, we take the 15,840 and we subtract it from 18,480. We're going to get 2,640. And then we're going to add on the minus 154 T1. Now we can combine these two, and we're going to get 0 is equal to 2640 minus 77 T1. Solving for T1, because it's our only unknown here, okay? So we're going to move this to the other side. 2640 negative is equal to negative 77 T1. Divide by 77 on both sides. Our T1 is equal to, make sure you can get 34.29 seconds. Okay. Did you guys get that? So T1 was how long did it take for our police car to accelerate to 105? It looks like Drew got it. Excellent. Thank you. Nia got it. Brooke got it. Good, good, good. All right. So that's the time. We're not done yet, right? Jason got it. Excellent. We're looking for the acceleration AB. Oh, but look, we just got T1. So we can use this equation and plug it right back in and solve for AB. Okay. So we're going to use that equation again. AB is equal to 154 divided by T1, but now we know T1. So it's going to be 154 divided by 34.29, right? So our AB is going to be equal to 4.49 feet per second squared. This we put a box around because that's what we've been trying to find. And then just verify that you get the 4.49. All right. Let's do a quick review because that was a pretty long problem to see really what we did here. Okay, and just kind of wrap this up before we stop. So starting at the beginning, okay, we'll kind of look at our illustration here. We have a car, 90 miles an hour, steady, 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 all the way, right? Police car starts out, accelerates to 105. Police car catches at that 3 mile mark. Okay. And we want to know what was the original acceleration here of our car. Okay. So first things first, we identified what we knew. Okay. For each one of the cars, the car itself, and then the police car. We also said all of our units are English units and we need them to be in feet and seconds. The problem gave things to us in miles and hours. Okay. So first thing we did was we converted the miles per hour into feet per second for the velocities that we were given, and then the distance of 3 miles into feet. That way, going forward, using these numbers, we didn't have to worry about putting units in and cancellations and all that kind of stuff. Okay. We analyzed first the motion of the car to determine what was the final time where the 3 mile mark was, where the two cars caught up to each other. Okay. Then we looked at the motion of car B, which had two parts: constant acceleration until it got to that 105 miles per hour, and then constant velocity, no acceleration after it hit that. Okay. And we wanted to find out what was the acceleration, of that car B. So doing both sides, okay, and then adding up those two distances to get the total of 3 miles. Our unknown here ended up being the times, because we wanted to know how much time did it take for that police car to accelerate to that 105. Once we had the time that it had was to accelerate to that 105, now we could find out how fast was it accelerating during that stretch. And it's 4.49 feet per second squared. Okay. Make sure as a final answer, when you report the final answers, that it has the correct units, you have your box around it, and that the variable is identified here. So don't just at the end of the problem put 4.49 feet per second squared and put a box around it. No, tell me what that is. And it's the acceleration of car B, which is the police car. Okay. All right. Any questions before I stop recording? Okay, doesn't look like there is. So what I'm going to do is I'm going to stop recording at this time.